Hi kids, welcome to my very first video for IB Chemistry 1. Discussion 1-1, we're going to talk about atoms. Alright, so imagine for a second that you have a piece of copper. If you take that piece of copper and cut it in half, you're going to have two smaller pieces. If you take one of those pieces and keep cutting in half, cutting in half, cutting in half, cutting in half, if it gets smaller and smaller and smaller. So is there a point when it's so small you cannot break it apart anymore? And the answer for that is yes. Once you get to that point when you have the smallest possible unit of something you can still call copper, we call that an atom of copper. So this here is a model of an atom. We can see that we have protons and neutrons contained in the nucleus of the atom with electrons swirling around the outside. Now this model of the atom is fairly ubiquitous. People have seen this before, but it doesn't really represent the actual structure of an atom. So just so you guys know, Ernest Rutherford's gold foil experiment is no longer part of the high school standards, but it does help me to help explain what atoms actually do look like. So I'm going to talk about it really briefly. So what Rutherford did was he shot these little positively charged radioactive particles called alpha particles at a piece of gold foil. We'll talk about what an alpha particle is in topic 1-2. Now gold foil is just like aluminum foil, but instead of being made out of aluminum, it's made out of gold. Now Rutherford's hypothesis came from earlier models of the atom. So everybody before Rutherford thought that atoms were solid spheres, and that if you lined up a bunch of atoms together, it would almost make like a wall that nothing could get through. So Rutherford's hypothesis was that the alpha particles would bounce off the gold foil, just like throwing a tennis ball against a brick wall. You would expect that ball to bounce off. And so here's just a model of Rutherford's experiment. We have the particle emitter here. He fired those particles at the gold foil, and all around is a detector. So this is a model of his results. The yellow lines here represent the path of the alpha particles, and the orange circles represent gold atoms. So if you see this little black dot in the center of these atoms, that is the nucleus of the atom. And what he found was that most of those alpha particles were able to pass directly through the gold foil with very, very little deflection. It was almost like the atoms weren't there at all. But he did see a very, very small fraction of those alpha particles get deflected by something or shot right back out, back at him. So again, most of those particles passed right through the foil with no deflection. That told him that atoms are actually made up of mostly empty space. But the fact that a very small number were deflected told him that there was a solid bit inside an atom. And that solid bit was the nucleus of the atom. Now compared to the size of an atom, the nucleus is actually really, really, really tiny, like super, super tiny, but it contains like 99.9999999% of the mass of every atom. So just think about this for a second. If the nucleus of an atom were the size of a marble, and you put that marble on the 50-yard line of a football field, the size of the atom itself would be as big as the football field, while the nucleus would be the size of that marble. Other people have said the difference between the size of the nucleus of an atom and the overall size of the atom is like comparing the moon to the sun. Really, really small. All right, so let's talk briefly about elements versus compounds. Elements are the raw building blocks of the universe. There's no more elementary particle that we can see with our own eyes than an element, okay? Now, elements cannot be broken down into simpler substance. That's what it means to be elementary. You're the most simple you can be. That's why elementary school is what the first level of schooling is. Now, every element in the universe, there are 118 total, are all found on the periodic table of the elements. 92 of those elements occur naturally. We'll actually talk about how they're made in topic 2, and several of them are man-made. Now let's talk about a compound. A compound is a substance that's made up of different atoms that are chemically bonded together. So I'm just going to switch to my document camera to just illustrate the difference between elements and compounds. So if you looked at your periodic table, you'd see that one element on the periodic table is hydrogen, and hydrogen has a symbol H. Another element on the periodic table is oxygen, which has the symbol O. Now these are individual elements represented by only a single symbol. But if we take two hydrogen atoms and chemically bond them to the oxygen, we get a compound called water. So the analogy I like to use in class is think of the element being the ingredients in a recipe. If we were going to make cookies, your recipe would include things like flour, butter, eggs, vanilla, etc., etc. Once you put all those ingredients together, you make a more complex structure called a cookie. Well, elements are the ingredients for making compounds. When we take these simple elements and combine them into more complex structures, we get what are known as compounds. Now, one thing I think that is important to note is that compounds do not have the same properties as the elements from whence they came. So just to go back to the water example, hydrogen is a clear, colorless, odorless gas that's very, very good at burning. If you put a flame to it, it bursts into flames. Same thing with oxygen. It's a clear, colorless, odorless gas that's very, very flammable. If you put a flame to pure oxygen, it goes up in a flash. Water, though, is a liquid at room temperature. Water does not burn. Water, even though it's made of two clear, colorless gases, does not have the same properties as the elements that it comes from. Another example of that is sodium, chlorine, and sodium chloride. So if you're in class, I'll click these and give you a little video, but these are links to other YouTube videos, and I don't want to get dinged for copyright infringement. So I'll just tell you, sodium is a really strange element. It's a soft metal, and it reacts violently with water and air. If you throw it into water, it'll sputter around on top of the water. Eventually a flame will appear, and poof, it'll explode, basically. So if you eat sodium, you're going to have a very, very bad day. Chlorine is a greenish-yellow gas. Now, sodium and chlorine are both elements that you can find on the periodic table. And when chlorine is inhaled, it will react with the water in your lungs and produce hydrochloric acid, which would dissolve your lung tissue and be a very painful way to go. Chlorine was actually used as a chemical weapon back in World War I. They stopped using it because they found they couldn't really control the wind, and sometimes when they released that chlorine, the wind actually pushed that gas back into their own trenches. Now, when sodium is exposed to chlorine, a really cool and violent chemical reaction occurs. That causes the sodium and chlorine to come together to form a compound. That compound we call sodium chloride. And sodium chloride is table salt. So sodium, element, metal that explodes when it touches water. Chlorine, gas that forms a dangerous acid when it touches water. Sodium chloride is food. Okay? So just to summarize what we talked about on the previous slides, elements versus compounds, you can see these diagrams. Elements will be only made up of one type of particle. So you can have either what's known as a monatomic element, where there's single individual atoms, or diatomic elements. And we'll see examples of that on this slide. So elements are made up of atoms. Atoms are the simplest form of matter. Now, there are more fundamental particles than atoms, but if you want to learn about them, you're going to have to take a physics class. Now, atoms cannot be broken down into simpler substances. Once you have that atom of copper, you can no longer break that down into any simpler bits. You'll find all elements on the periodic table, and you can recognize the formula of an element because the symbol will be made up of only one capital letter. So just some examples of that. Oxygen. There you go with that diatomic element. Even though there are two oxygen atoms bonded together, it's still considered an element because both of the atoms are oxygen. And you can recognize that because there's only one capital letter in that formula. Another one is sodium. I already mentioned that. Sulfur, or hydrogen, another one of our diatomic elements. So compounds are made up of the smallest unit of a compound is called a molecule. So again, going back to my water example, I have hydrogen and oxygen atoms that come together to make water molecules. Now, molecules contain atoms of different elements chemically bonded together. So if it's two atoms of the same element bonded together, it's still considered an element. But if there's atoms of different elements bonded together, then we would call it a compound. So compounds can be broken down into simpler substances. You can break them apart into the atoms that make them up. And you can recognize the symbol or the chemical formula for a compound because it will be made up of more than one capital letter. So things like water, carbon dioxide, glucose, or sulfur dioxide. All right, now let's talk about the bits that atoms are made of. Atoms are made of particles called subatomic particles. They're particles that are smaller than atoms, hence subatomic. So there's three subatomic particles: protons, neutrons, and electrons. And these little symbols in parentheses are how we denote protons, neutrons, and electrons. Now, the next thing we're going to talk about is where they're located in the atom and their relative size. So the proton has a mass, or size, if you will, of 1 atomic mass unit. Now, don't worry about AMU. It's just an acronym for atomic mass unit, and it's just a way to measure the mass of very, very small particles like protons. Now, protons live in the nucleus of the atom, like I mentioned before. Neutrons have a mass of about 1 atomic mass unit, and they exist in the nucleus of the atom as well. So we can see here that protons and neutrons have about the same size. Now, if you express the mass of an electron in AMUs, you'll see that an electron is 1/1836th of an AMU. In other words, it would take 1,836 electrons altogether to equal the mass of 1 proton or neutron. So the overarching theme here is that protons and neutrons are about the same in size and mass, and electrons are very much smaller. So I mentioned before that the majority of the mass of an element is contained in that very, very small, very, very dense nucleus because the heaviest particles are located in that nucleus. Now, the charges of these particles are indicated in their symbols, but we can also quantify that charge. A proton has a charge of +1. Neutrons, not shockingly, are neutral, and electrons have a charge that is equal and opposite that of a proton. So you're going to see as we go on in this discussion that atoms, by definition, are neutral because all of the positive charges in an atom have to balance out all the negative charges in an atom. So again, here's just this image of an atom. We have protons and neutrons in the nucleus. Of course, to make this model be more realistic, we'd have to shrink that nucleus down so small that you wouldn't even be able to see it on your screen. Now let's talk about isotopes. For a long, long time, scientists, and before them, alchemists, believed that atoms of the same element were identical to each other in every single way. Now, we know that this is not true. Atoms of the same element will always have the same number of protons, but can differ in the number of neutrons in the nucleus. When this occurs, when we have atoms of the same element that have different numbers of neutrons, those are called isotopes. Now, since they have different numbers of neutrons, and neutrons contribute to the overall mass of an element, isotopes of the same element will contain the same number of protons, but will have different numbers of neutrons and thus different masses. And you can see that difference in mass by looking at the names of individual isotopes. So now let's talk about naming isotopes and isotopic notation. This is the general form for the symbol of every isotope. We have a X as the symbol of the element with a superscripted A and a subscripted Z. The superscripted A is known as the mass number. And the mass number is just the sum of all the protons and neutrons in the nucleus of an atom. Let me break out my periodic table here. So because the mass number, sorry I'm making a mess here, because the mass number is just the sum of these subatomic particles, the mass number is always going to be a whole number. But if you look at the periodic table, let me hit the focus again. Come on now. There we go. There we go. All of the masses for the elements are decimals. This should tell you that the periodic table does not give you the mass number. We'll talk about what the periodic table gives you later in this discussion. The Z is known as the atomic number, and the atomic number corresponds to the number of protons in the nucleus. Now the significance of this, again, if we turn back to our periodic table, the atomic number, according to the key, is this number below the symbol. Every element has its own unique atomic number. So the significance of this is huge. That means that the number of protons in the nucleus of an atom determines what that atom is. If your nucleus has 6 protons in it, that means you're carbon. If you're somehow able to jam another proton into that nucleus, now you'd have 7. That element would magically turn into nitrogen. All right, so let's look at how we count the numbers of protons, neutrons, and electrons in an atom by looking at isotopic notation. So I see down here, this is called carbon-12. If I look at the atomic number down here in the bottom left tells us the number of protons. And again, if I go back to my periodic table, you can see for carbon, the atomic number is 6. That means there are 6 protons in the nucleus of a carbon atom. Now, as I mentioned before, if you know how many protons are in the atom, you also know how many electrons are in the atom. Because however many positive charges you have to have equal numbers of negative charges. So 6 protons means 6 electrons. Now, to get the number of neutrons, we have to look at the mass number. The mass number is the sum of protons and neutrons. In other words, it's the total number of subatomic particles in the nucleus of the atom. If 6 of those subatomic particles are protons, and there's 12 total, then 6 of them would have to be neutrons. So all you have to do to find the number of neutrons in an isotope is subtract the atomic number from the mass number. So take a minute, pause the video, see if you can work out how many protons, neutrons, and electrons are in an atom of carbon-14. All right, hopefully you paused the video and worked this out. It's carbon, the atomic number is 6, so protons and electrons are still going to be 6. Now though, we have 14 particles in our nucleus, and 6 of them are protons, so 8 of them must be neutrons. Okay, moving right along. So what information does the periodic table give us about atoms? Again, the periodic table will not give us the mass number for any particular isotope because elements have multiple different isotopes. It does give us the atomic number. Of course, that corresponds to the number of protons. We have the element symbol, the element name, and this mass down here. Now, the mass that's on the periodic table is not the same as the mass number. That mass we call relative atomic mass, and it's denoted with a capital A with a subscripted R. Now, the relative atomic mass is the weighted average for all known isotopes of a particular element. So different elements have different numbers of isotopes. We take an average of the masses of all the isotopes, and we add them together. Sorry, I had a little brain fart there. That is why the mass on the periodic table is a decimal and not a whole number. Really try to internalize this. The mass on the periodic table is not the same thing as the mass number. All right, so again, I'm going to put up a couple of practice problems here. I want you guys to pause the video, use your periodic table on Google Classroom, and try to work these out. So I'm just gonna kind of click up the answers right now, and hopefully you will have paused the video and actually tried this before getting the solution. So barium is atomic number 56. That means 56 protons and electrons. I cannot stress enough, both of those come from the atomic number. Now barium-137, this 137, a lot of kids confuse that with the atomic number. But remember, there's only 118 elements, so it couldn't have an atomic number of 137. This 137 is the mass number. So again, in order to find the number of neutrons, I have to subtract the number of protons from the mass number. So in this case, we get 81. All right, so this table has 4 different columns for 4 different elements. Each column contains enough information for you to fill in all of the boxes. Shh, I'm recording a video, bubbies. So I'm going to go through one of them really slowly, and then I'm going to have you guys do the rest and check your work. So when I see this symbol, this is the symbol for phosphorus 32. This number is a superscript, and remember the superscripted number is the mass number. That means there are 32 particles in the nucleus of a phosphorus 32 atom. So let's go to our periodic table and find phosphorus. There it is. I see it has an atomic number of 15. That means, let me go back to my discussion, that there are 15 protons and 15 electrons. The mass number is given to us in the formula. The mass number is 32, which means there must be 17 neutrons. You can always check your work, because if you add up the protons and the neutrons, they should add up to the mass number. So again, pause the video, fill in the rest of the table. This video is going long and we still have to get to the hardest bit. So what I'm going to do is just have you check your work. If you have any questions about these, then bring them to me in class or come see me after school one day. Boom, 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 boom. There they are. Take a moment, take a screenshot of this. If you made any errors, go back in the video to see how we do this so that you can learn how to get the correct answers. All right, so how do we calculate the mass that we see on the periodic table? To do that, we use the following form. Well, I'll actually explain it first. So if we see the problem here, it says silicon has 3 naturally occurring isotopes, silicon-28, silicon-29, and silicon-30. The masses for each isotope in AMUs are given as well. And it gives us a percentage. This percentage is what we call the natural abundance of each isotope. So what this 92.21% for silicon-28 means is that of all the silicon in the universe, 92% of it is silicon-28. 4.7% of it is silicon-29, and 3.1% of it is silicon-30. So the formula we use to actually calculate that mass looks like this. Recall that A sub R is the symbol for relative atomic mass, and the formula is the mass of the first isotope times its percentage in decimal form plus the mass of the second isotope times its decimal percentage plus dot dot dot. The plus dot 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 is because this formula will change depending on how many isotopes you have. So all we're going to do here is use these data to calculate the atomic mass of silicon. So here is the formula adjusted for our actual problem. Here is the work, the mass of silicon-28 times its decimal percentage. Again, to take a percentage into a decimal, you just divide by 100, which moves the decimal place to the left 2 places. When you add all these factors together, you get 28.09 atomic mass units. If you compare that with what's on the periodic table for silicon, 28.09. So that is where those numbers come from. It is a weighted average of all of the masses and abundances of all the isotopes for a particular element. All right, so this is not the way you are going to really be solving these problems in IB Chem 1. You're going to see problems that look like this. Chlorine has 2 isotopes, chlorine-35 and chlorine-37. The average atomic mass is 35.45. Determine the relative abundances of each isotope. So instead of asking you guys to calculate the mass, we give you the mass and ask you to calculate the abundance. So I don't have any transitions on these slides. I'm just going to do this out for you guys on my whiteboard here. So So to solve these problems, we need to create what's known as a system of equations. And a lot of you guys, all of you guys actually did this in Algebra 1. So this should ring a couple of bells. First thing I'm going to do is write the formula we'll be using. A sub r will be equal to the mass of chlorine 35 times its decimal percentage, plus the mass of chlorine 37 times its decimal percentage. So we're going to have two variables in our equation. Oh snap. We got to take those two variables and use a system of equations to bring them into one. So I'm just going to go ahead, remember this, let x equal, right? So let's let x equal the percentage of chlorine 35. Remember, we're dealing with percentages. If you have more than one percentage, they're always going to add up to 100. In this case, they're always going to add up to 1 because we're using decimal percentages. So let's let y equal the percentage of chlorine 37. Now here's our first equation in our system of equations. Because these are percentages, we know that if you take variable x and add it to variable y, they're going to add up to 1. So what we want to do is express our variable y in terms of x. So to do that, I'm going to subtract x from both sides of the equation, and this equation then becomes y is equal to 1 minus x. So I can actually change this y from y to 1 minus x. Now it's just a matter of plugging these values into our equation and solving for x. All right, bring the laughter down a little bit there, bubbies. I'm trying to teach here. Thank you, sweetie. Okay, so A sub r is the relative atomic mass. The problem told us that chlorine had a relative atomic mass of 35.45 atomic mass units. We're then going to plug in the mass of chlorine 35. We're just going to use the mass number here of 35 times the percentage of chlorine 35, which we call x. To that, I'm going to add the mass of chlorine 37, which is 37, and multiply by the percentage of chlorine 37, which we defined as 1 minus x. Now, it's just a matter of solving for x. Derby, come on. Everybody's making this video harder for me. So I'm going to go through and simplify this by changing the color too. So 35.45 equals 35x plus, now I have to distribute this 37 inside those parentheses, so plus 37 minus 37x. So now the first thing I'm going to do is eliminate these whole numbers. So I'm going to subtract from both sides 37. And I'm going to combine these two factors in terms of x. So what we're going to get when we do this, I've done this problem a million times and I still don't just remember or trust myself. On this side of the equation, when we perform this calculation, I get negative 1.55 is equal to, when I combine the two x terms, I get negative 2x. Now to complete this equation, I'm going to divide both sides by negative 2, which gives me an answer for x of 0.775. We defined x as the percentage of chlorine 35, so that's our answer for chlorine 35. Now, y is a different story. Y was 1 minus x. So when we're finding the percentage of chlorine 37, we're going to subtract 0.775 from 1, so I get that y is equal to 0.225. And these are your two abundances. Now, these are percentages in decimal form. If you feel more comfortable converting these into percentages, feel free. It would be 77.5% and 22.5%. Okay, so that's our first example. On the next and final slide, I want you guys to try this all on your own. Use what I just did and the notes you got in class as your guide. So you should pause the video at this point. I'm just erasing my whiteboard. All right, so this problem says that neon has two naturally occurring isotopes, neon 20 and neon 22. The relative atomic mass of neon is 20.179. Calculate the natural abundance of each isotope. Same type of problem, different numbers. So for this one, I'm going to go through it a little bit quicker because I expect you guys have already completed this and completed it correctly. I'm actually going to go back to the mass because I already forgot it. So the relative atomic mass of neon is 20.179, and we have neon 20 and neon 22. Boom. All right, so when I define my variables now, actually I'll define my variables before I get started there. Let's let x equal the percentage of neon 20, which means 1 minus x will equal the percentage of neon 22. Again, once you get used to doing these, you're going to be able to bust them out really quickly because it's the same thing every time. So the relative atomic mass was 20.179. That's going to be equal to the mass of neon 20, which is 20, times its relative abundance, which is x, plus the mass of neon 22 times its abundance, which is 1 minus x. Again, I'm going to simplify this by combining like terms. So 20.179 equals 20x plus 22 minus 22x. So now I'm going to isolate my variable and solve for x. First thing I'm going to do is subtract 22 from both sides of the equation. That gives me negative 1.821 on the left side of the equation. And I combine my like terms containing x, and that gives me negative 2x. Now to solve for x, we're just going to divide both sides of the equation by negative 2. That gives me a value for x of 0.9105. Of course, our other variable, y, is just 1 minus 0.9105, which is equal to 0.0895. Now again, you can convert these into percentages you want. So the percentage of neon 20 is 91.05%, and the percentage of neon 22 is 8.95%. Now the last thing I want to mention is how you can look at your answer and determine whether or not your response makes sense. Yeah. Well, the atomic mass of neon is 20.179, and 91% of all the neon in the universe has a mass number of 20. So we should expect our answer to show a greater amount of neon 20 than 22, and indeed it does. All right, so that's it for discussion 1-1. If you're watching this video, thank you for sticking through to the end. I'll see everybody in class, and bring any questions you have. No question with this topic is too silly. Have a good one. Thank you.